In the last video we derived this algorithm, but it isn't complete because we don't know how to do the addition and subtraction of our 32-bit floating point numbers. Now, something that I never mentioned in the last video was this little circle. So the little circle stands for the rounding. So we would add and subtract the numbers and then we would perform the rounding, but we're not going to cover the rounding until a later video. So the question is, how do we add and subtract these numbers? Well, these numbers in the floating point representation is going to have a mantissa for x, it's going to have the base, and it's also going to have the exponent for x. And again, it's going to have the mantissa for y, the base, and the exponent for y. And we want to know how to do the addition and subtraction of this section here. So that's what the rest of this video is about. So in order to work out how we're going to do this addition and subtraction, we'll make a comparison to the decimal system. And we'll look at a couple of examples here. Now let's say, for example, we have the number 2.35 times 10 to the 6. So that's our x value. And our y value is 7.45 times 10 to the 3. Now, if we were going to add these together, we couldn't simply add the 2.35 and the 7.45. And we can see that because if we were to extend this out and just write it without the exponent, then this number would be 235 and there would be 1, 2, 3, 4 zeros. And this number here would be 7450. And in order to add these, we would have to position the 7450 at the end here. This is going to be our units, tens, hundreds and thousands. So we would position that 7450 and then the 235 and the 4 zeros. We would add them together, we would get this number here. And then we could put it back into our exponent format. And that would be our value 2.35745 times 10 to the 6. So we would just be taking our full stop here 6 places along, 1, 2, 3, 4, 5 and 6. So what we want to do is we want to make the exponents the same before we do the addition. So that means we could make the smallest exponent equal to the largest exponent, or equally we could make the largest exponent equal to the smallest exponent. So the route that we're going to do here is we're going to take the smallest exponent and we're going to increase it to the size of the largest exponent. Now, whenever we do this, we're going to have to then reduce the size of the mantissa accordingly. So let's say y has the smallest exponent, which is a value of 3. So we're going to make that exponent a value of 6. So in effect, we'll have increased the number by 1000. So in order to get the correct number, we're going to have to then decrease the mantissa also by a factor of 1000. So if we take the value for our y, which is 7.45 times 10 to the 3, then we're going to increase that 10 to the 3 to 10 to the 6. So that's an increase of 1000. So in order to make the number the same, we're going to have to decrease the mantissa here equally by a value of 1000, such that we've got our 7.45 times 10 to the 3, and it's going to equal 0.00745 times 10 to the 6. So that means that by making the exponents the same, we can have the exponents here 10 to the 6, exponent is 10 to the 6. So whenever we add these two together, we're going to get our 2.35745 times 10 to the 6, which is the same as what we have above. Now you'll notice in example 1 that we had to increase the value of the exponent by 1000 and decrease the value of the mantissa by 1000. In example number 2, you'll notice that the y value actually has a larger exponent than the x value. So that would mean that if we were to realise this in an actual circuit, we would have to swap the values for our x and the y. Because the circuitry that we would have access to and designed will make the exponent larger and the mantissa smaller. And in order to get the right answer, we would have to therefore ensure that we were using this value here. This would be making the exponent of x larger and the mantissa of x smaller. So what we can do in order to reuse that one piece of circuitry is just swap the values for our x and y. So that is, we want to ensure that the exponent for x is always greater than or equal to the exponent for y. Now we could do it and have two lots of circuits, and we could have a circuit that could make the exponent larger or smaller and the mantissa larger or smaller. But in order to cut down that amount of circuitry, we only need to ensure that we swap the values here, x and y, at the inputs to our circuit. So this ensures that our circuit only ever has to increase the exponent and decrease the mantissa. So it simply makes the circuit smaller and a much easier and neater design. Also notice here in the answer, the value for the exponent is going to be the largest exponent value. So in this case here, it would be 10 to the power of 6. And the largest exponent value we know is always going to be the x exponent. So we can just set the answer tentatively to the value of e to the x. So let's go to the next page and we'll summarise what we've learned here. And we'll be almost finished on with our basic algorithm. So don't worry too much if you're not too keen on the mathematics. In the next video we will go into Excel and we'll start chasing up individual ones and zeros, and we'll be able to see by our own eyes exactly how this is going to work. But it's worthwhile writing it down mathematically because this is how you'll tend to see it in books, and it gives you a good introduction to the mathematics employed in our 32-bit floating point arithmetic. So we've seen the algorithm that we're going to use here, and we're adding x and y, and we're going to get the summation here, so it'll be the mod of x. So this is really just the value of x but without the sign, so it's just made positive. And again the same with y. And the minus 1 s to the z is going to tell us whether we're going to add or subtract. And when that adding and subtracting has been done, the actual sign of the answer is going to be given by this term here. Now we said just in the previous page that first of all what we want to do is we want to ensure that our value for our ex is greater than or equal to our ey. And we said we wanted to do that really just to simplify the circuitry. So this would ensure that we're only ever increasing the exponent and decreasing the mantissa. Now secondly, we want to align the mantissas before we do the adding or subtracting. And this is the little bit of mathematics that tells us we're going to align the mantissa. So we've got an example down here. So in the previous page we had 7.45 times 10 to the 3, and what we did is we increased this by 1,000, so the exponent went up by 1,000, and then we decreased the mantissa by 1,000. So what we have here, the my, is just equivalent to this number here, 7.45, and the beta is the radix, and it's a value of 10. But of course in this example here we're using decimal just to make it simpler for us. In floating point arithmetic, the base is obviously going to be a base of 2. So we wanted to increase this from 3 to 6. So what we wanted to do is we wanted to change the mantissa and we wanted to decrease it by the difference between these two numbers. So for example, we wanted the value of our my to decrease. So our my is going to decrease by the value of the e to the x, that's the largest exponent, minus e to the y. So in this case, e to the x and e to the y is going to be 6 minus 3. So we wanted to decrease this here by 6 minus 3. So in order to decrease it, we're going to have it as a minus. So you'd end up with our value my, and it would be beta to the minus 3. And that's just saying that we're going to take this value here and we're going to shift the decimal point 3 positions in this direction here. Okay, or equivalently, we're going to take the number and we're going to make the number 1,000 times smaller, and that's why you've got the minus sign here. So that's a little bit of mathematics. It tells us that we're going to do a significant alignment. Now we also said that we're going to set the result for the exponent as a value of ex, because that's going to be the largest exponent value. And finally, or the fourth term here, we're going to work out the mantissa for the result. So the mantissa for the result we're going to get from what we have up here is going to be the mantissa for the value of our x. And we're going to either add or subtract the mantissa for y, which has been already had the significant, or that the mantissa has already been realigned. So this is the realignment. This whole thing here is going to give us our value of mr, and we know the value of our exponent. The exponent is going to be our value e to the x, so we'll just call that er. And finally, the actual sign is going to be given by our minus 1 to the power of sr, which we really just get from this minus 1 sx. So this is the mathematics. This is how we write the mathematics out. There's one other thing that we have to do, is we're going to have to normalize this, because we've already shifted the mantissa in this instance here by a factor of 1,000, or 3 places. So in order to normalize it, we're going to have to shift the mantissa back to its the correct position. So these are the 6 basic steps that we need to follow through in our algorithm, and we have to build a circuit that's going to do this for us. Now you'll see in a lot of books that they'll write this algorithm out and this will be the end of the story, but of course this is just the most basic description. We've still got other things we're going to have to take care of. For example, when we normalize the result, we may have to change the value for our exponent. Also, whenever we work out this value for mr, there are situations in which the value within this bracket is actually a negative value. In that case, what we have to do is we just have to negate it and make it positive, because the final answer for the sign is only going to be given by what is outside this bracket. But we'll see that whenever we look at the next video and we start to look at the actual addition in detail. Also, the way that we normalize the result will be different depending on whether the exponent values are different by greater than a factor of 0 or 1. So if they're different by a factor of greater than 1, then we have to create a leading 0 counter, and we have to do the normalization through the leading 0 count. Also, this description here doesn't really tell us anything about the general architecture that we're going to use in order to create our adder and subtractor. Finally, it doesn't tell us anything about subnormal numbers, and it has got nothing in it about rounding. So there's still quite a lot of stuff that we're going to have to cover in order to build up our fully functioning 32-bit adder and subtractor, which will adhere to the IEEE 754 standards. But we'll get onto that through the rest of the course. We've come quite far here. We've covered an awful lot of the initial difficulties, and we've written the problem out and a solution out mathematically. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.